So at this point, what I want to do is I want to recall what we did in the last video, and that's that the natural log of 1 plus x could be written as a power series of negative 1 to the n times 1 over n plus 1 x to the n plus 1. And there's a few implications here. The first implication, and this is something that I've actually told you about before, whether or not we think about it like this, it doesn't matter. But the first implication is actually, think about what happens when we plug in, say, x equals 1. So if x is equal to 1, on the one hand, we get the natural log of 2. On the other hand, if x is equal to 1, then all of these terms are going to be 1 to a power, and they're all 1. And so we're going to have the sum from 0 to infinity of negative 1 to the n, 1 over n plus 1. And what the sum is going to be is, this is just the alternating harmonic series, just written, kind of, we shifted the index a little bit here. So we have a not quite 1 over n and we're starting at 1, but we have a 1 over n plus 1 and we're starting at 0. But same idea. This is going to be 1. When n is equal to 2, I'm sorry, when n is equal to 1, we get minus 1/2, and then plus a third, minus a fourth, plus a fifth, and so on. And so when we were talking about the geometric series, this alternating harmonic series came up, and I kind of offhand mentioned that this converges to the natural log of 2. We just saw that using the power series representation for this function, natural log of 1 plus x. Now, I'm slightly cheating here because the natural log of 1 plus x we wrote as a power series when the absolute value of x is less than 1. It turns out that in this case, and in this case, I shouldn't say in this case only, but it's not true in all cases, but it is true here. You can plug in x equals 1 and it turns out everything's fine. And that's because when x is equal to 1, the series still converges. It's just that it converges conditionally. And so this series that we're going to get still is going to be the natural log of 2. And if you add up these terms enough, you get the natural log of 2. Likewise, if I were to look at, say, arctangent, we also saw in the last video that arctangent is going to be the sum from 0 to infinity of negative 1 to the n, 1 over 2n plus 1, x to the 2n plus 1. And so now let's think about what is arctangent of 1. So let's do the same idea here. If x is equal to 1, arctangent of 1, in other words, the value that you have to plug into tangent to get 1 is going to be pi over 4. And so this is going to be written as a series, n equals 0 to infinity, negative 1 to the n, times 1 over 2n plus 1. And again, this original series is really only going to be valid when x is less than 1 in absolute value, but it turns out it's also valid at 1 because you get this alternating series behavior. Everything's fine. In this case, it's actually also valid at negative 1. Whereas in the previous case, you'd have two problems. When you plug in negative 1, you get natural log of 0, and there's problems already. But also, the series doesn't converge when x is negative 1 because you have negative 1 to the n plus 1, and then negative 1 to the n. And so altogether, you get negative 1 to the 2n, which is going to be 1. And so that's what you get is negative 1 over n plus 1, as n goes from 0 to infinity. And that's just the harmonic series, and that diverges. Okay, that makes sense. That agrees with the fact that this natural log of 0 is undefined. Basically, natural log, as your inside goes to 0 from the right, is going to go to negative infinity. Okay, and so that series kind of agrees with that. If you think about it, we had negative 1 times the harmonic series. So that's going to go to negative infinity. At any rate, what this series does, now I'm looking back at the arctangent, plugging in x equals 1, this gives us a formula for pi. So pi over 4 is equal to the sum from 0 to infinity of negative 1 to the n times 1 over 2n plus 1. And so if I move the 4 from the left side to the right side, we now have a series okay, that we can use to represent pi. And if we want to get values of pi accurate to however many decimal places, we just need to add enough terms of this series. Historically, values of pi, so going back to the Greeks, pi is defined as the ratio of the circumference of a circle to its diameter. Okay, so if we take a circle, the ratio of the circumference to the diameter turns out to be constant no matter how big the circle is. And that constant ratio, that constant multiple is pi. That's what pi is. And so to measure this, what the Greeks would do is they would basically take a circle, and then what they would do is they would inscribe the circle inside another shape. Okay, so maybe they would take it and put it inside an octagon of appropriate sides. I can't draw, but these are all supposed to be tangent. And so then you could measure the perimeter of the octagon, and you knew that pi had to be less than that because pi was that circumference. And you could also put on the inside some other shape, maybe a six-sided shape, something like that. You could measure that shape. And then you had kind of a bound for pi. It had to be between basically the circumference of the inner hexagon and the circumference of the outer octagon. Okay. And then the more and more sides that you had, the better approximation you would get. The problem is that that's a very tedious method to calculate pi by hand. Although, I mean, it's a method that can be used, so it's noteworthy for that reason. And that, you can use that to estimate at least what pi is up to a couple digits. But it turns out using series kind of changes the nature of the game. If you want to use a series representation for pi, you can figure out pi up to basically as many decimal places as you want if you add enough terms from the sum. So if you want to compute pi to 1,000,000 decimal places, you just have to compute enough terms of the sum. We haven't explicitly talked about remainders and how to use the different convergence tests that we've talked about in class to estimate values. And I was planning on doing that in the last week or two of class. But it turns out that in practice, this series in particular is not a great series for representing pi because this is an alternating series that it just converges too slowly. Okay, this series by the name was invented or discovered by a mathematician named Gregory. So this is called Gregory's series. Gregory was the mathematician's last name. And so this is called Gregory's series. So this is the series for pi over 4. But it's just super, super slowly converging. I think if you want to get pi to like 4 decimal places, you need something like 1,000,000 terms. I mean, it's just obnoxiously slow. I forget exactly the numbers here. But if you want a pi to, let's see, I could think about this for a second. If you want a pi to be 1,000,000 places, I'm sorry, if you want a pi to be accurate to say 4 decimal places, you would need something like 10,000 terms is what it actually is. So it's just by hand before there were calculators. This is just a terrible way to calculate pi. Newton found some ways of getting other series for pi that are a little bit faster converging. And then a mathematician named Ramanujan came up with another series for pi. And this is a just super rapidly converging series. And it's so crazy that I just want to share it with you. And so here, Ramanujan was a very, very interesting Indian mathematician. He died very young. He was kind of a prodigy. He had no formal education at all. He just had these formulas that came to him somehow. And he showed, or at least he wrote down, that if you take the series 2 square root of 2 over 99 squared, and you add this as n goes from 0 to infinity of 4n factorial over n factorial to the 4th times 26,930n plus 1103, all divided by 396 to the 4n, that converges to 1 over pi. And now this is a super complicated series, way more complicated than Gregory's series was. But this converges way, way faster because you have powers here. This is not just, here you have like 1 over n. And so if you want this to be small, you just need n to be really, really big. Here, this goes to 0 very, very quickly. And so you can get a much more accurate representation of pi using this formula in formulas like it. This is just a crazy enough formula that I wanted to write it down and show you. Okay, so this is a formula from Ramanujan, probably from the 1910s or 1920s. Okay. So that's series being used to represent pi and natural log of 2. And that's one of the things that we can do with power series here. But one other thing I want to show you with power series, and here what I want to do is I'm going to stop sharing my notes. And what I want to do is I'm going to show you, I'm going to go through and we'll look at a graphing calculator here. Okay, so I'm going to go through and I'll share this screen here with the graphing calculator. What I want to do is I want to show you arctangent. Okay, so arctangent of x we know looks like that. We know that it, as x goes to infinity, it asymptotes at pi over 2, and the same as x goes to negative infinity. But on the other hand, we have a power series representation of arctangent. And we know that arctangent is going to be negative 1 to the n times 1 over 2n plus 1 x to the 2n plus 1. And so what I want to do is I want to start looking at different partial sums of the power series representation for arctangent. And so, for example, if n is equal to 0, we just get x to the 1. And that's, is, even though we're only using one term, that's a pretty good approximation for arctangent near the origin. And it turns out that the first term that you get from a power series representation is what you called back in section 2.9 of Calc 1. It's what you call the linearization of the function. It's basically the tangent line. Okay, so that's one thing that you can do. But we can do a little bit better. By adding more and more terms, we can get a power series that's going to be a good representation of this function, at least between negative 1 and 1. And so if I want a even better representation, what I could do is I could plug in n equals 0 and n equals 1. And so here we will get x and then minus 1/3 x cubed. Okay, and so here, that's actually an even better approximation for the function. Oops, it doesn't look right because it's not right. Minus 1/3 x cubed. There we go. So that's an even better approximation. So look at how closely that blue line hugs the curve, arctangent. I'm just going to zoom in here so that our x values are between negative 1 and 1. And notice that this is valid up to about, I don't know, negative 0.3, about negative 1/4 to 1/4. And if I were to look at this next term, x minus 1/3 x cubed, that's valid much longer. That goes to about negative 0.5 or negative 0.6 even. And the more and more terms that we add, so if I take negative 1 x cubed plus 1/5 x to the 5th, that's going to be an even better approximation between negative 1 and 1. Okay, and so just to zoom out, I don't actually care about what this function's doing away from the interval from negative 1 to 1. I know that this is just going to be a representation of the function between negative 1 and 1. So those are the only values where this is going to possibly be a good power series representation for us. And here we can take the 7th term. That's an even better approximation between negative 1 and 1. And then let's do one more. We'll do the 9th term. And the more and more terms we add, the better approximation we get. So that's negative 1/7 x to the 7th plus 1/9 x to the 9. And that's a better approximation still. Okay, so that's that. This one, it's not letting me edit this. I don't like that color. It's okay. Let's make it purple. That's fine. Okay, so that's an even better approximation of that function arctangent between negative 1 and 1. Okay, so this is the kind of thing that we're going to be doing in the next section, really, in 1110, is we're going to be talking about what are called Taylor series and ways that we can take basically any function. The natural log of 1 plus x and arctangent were nice because their derivatives were close to geometric series. But if you don't have that, if you have just like sine of x, for example, how do you use a power series to represent that function? And we'll talk about that. We'll handle that exact problem in 1110. Okay, so we will do that in the next section. But here's just some nice applications of our power series.